All right, a very good afternoon to all of you. And today we will talk about the foundation of formalism that's linked with the quantum theory. And we would like to talk about the basic 5 fundamental postulates of quantum mechanics. And these postulates, we should take them as the basic bone of the quantum mechanics, as a basic structure of a house. The whole of quantum mechanics, possibly the Schrodinger's wave equation, which is the basic equation for quantum mechanics, and what is true for us is that whatever discussions we have in this framework, in Schrodinger's framework, what we have here is we have a non-relativistic case. We are not discussing anything in the framework of relativity. As we understand, when we talk about relativity, then your particles have velocities close to the velocity of light. So this formalism is purely non-relativistic in nature, and we have the 5 fundamental postulates. They make the basic structure of quantum mechanics that goes on in the non-relativistic formalism. Obviously, we can add a 6th postulate also, which in certain cases is added because it also has its role in quantum mechanics, what we call as Pauli's exclusion principle. So the point is that what we have modern quantum mechanics. Okay, so what it says is that modern quantum mechanics is based on 5 fundamental postulates, and each postulate is explained with examples so that there is some clarification about the postulates. And postulates are always important. The first question arises in our mind that why we need a postulate. Now see, for example, yesterday I was talking about the failure of the classical physics, and I could give you an example of hydrogen atom problem. And what was the problem? The problem was the experimental observations. Okay, when we observe the spectrum of hydrogen atom, we have discrete states, right? But classical physics fails to understand, fails to explain the discreteness of energy levels. Because if we apply the classical physics, what we will observe? We will observe that electrons should continuously lose the energy, and it should fall into the frame of nucleus. So now Bohr is coming up with an argument. Okay, so he is coming up with an argument, and this argument is strange. Why is it strange? Because he is not explaining you why he is choosing the non-radiating shells. He simply chooses the non-radiating shell, and it works in the experiments, right? So postulates, they play a reference point for what you are trying to explain. Getting my point? So here we have the postulate, and we will try to inculcate some of the examples to understand these statements, these 5 important statements, whom we call as postulates of modern quantum mechanics. Right? So that's fine. Okay, now let's go with the postulate 1. Now, what the postulate says, it tells you that if you want any kind of information about the system, you have to represent that system by a state vector or by a wave function. Now this wave function or a state vector, it carries the complete information about your problem. It carries all the information. that your problem contains. And this state of the system, it belongs to a vector space. This vector space is an n-dimensional vector space. And this state of the vector is something that belongs to this Hilbert space. Right? So this is my postulate 1. So here what you are doing, you are starting your problem with a function. And that function is called the state vector, or it's called a wave function. Okay? Because we have the formalisms. Okay? You can have a state vector, it can have different meanings. Right? So what we call this, we call as ket. This is a ket of psi. Now, either if you have a wave function or you have a state vector, it carries the complete information about your system. It carries that information. See, it looks very classical at this point, that it tells you that it carries the all information. But we understand that this state vector does not have the physical implications. Okay, so this is point number 1. Now, if I have to take an example, rightly, I think we have solved this problem of particle in a box. You remember? Okay, so here you can see the electron is described by a standing wave that's spread across the box. You remember that particle in a box problem? What do you imagine there? That you have a wave that is spread across the one-dimensional box. And what you have, you finally come up with the state. You finally come up with the wave function of that problem. And that state is given by under root of 2 by L sine of n pi x by n. So what have you obtained here is the state of the vector. Right? A state vector, an eigenfunction. Electron has spin, right? Its spin can either be up or its spin can be down. So now you have to represent this by a state vector. You will represent the spin of an electron using a state vector. And you can write down the state of the spin state of an electron as a linear combination of two state vectors. Because there is a probability that the electron can have a spin up or electron can have a spin down. So here the state vector that you write down it's a combination, it's a linear combination of two states. But alpha and beta, they are the constants, and you calculate these alphas and betas using normalization condition. Okay, so normalization also falls in the postulates of the quantum mechanics. Is this clear? Okay, so this is it. Now, talking about hydrogen atom problem. In hydrogen atom problem, you have it is described by the quantum numbers. As you solve the Schrödinger's equation in spherical polar coordinates, you come up with these quantum numbers using the proper boundary conditions. So then, here you have the state vector. You have the eigenfunction or a state vector. That state vector is a function of the radial part, then angular part, then the azimuthal part, right? So this psi, which we solve in the framework of spherical polar coordinates, leads us to what? State vector. Now what is that state vector? It's something that carries all information of that system. It carries the all information of the system. That doesn't mean that you are obtaining the all information about the system. That's the difference here. Now, postulate 2. So postulate 1 is fine, okay? You have, for any system that you are trying to describe, you need to start that system with the state vector or an eigenfunction. And I quoted down a couple of examples that you understood what a state vector means. And it falls in the framework of the first postulate of quantum mechanics. Right. Now, postulate number 2. If I rightly tell you, in classical physics, we have observables, okay? And corresponding to each observable in classical mechanics, we have an operator in quantum mechanics. But here, what the postulate tells us about the observables, every measurable physical quantity corresponds to a Hermitian operator. Come on, right? So Hermitian operator we have already discussed. Okay? Now what is a Hermitian operator? An operator is Hermitian if the adjoint of that operator is equal to the same operator. That means if I have an operator, I take its complex conjugate, I transpose the elements of this matrix. If the complex conjugate and the transpose of the matrix element is same as that of the original operator, then I will call it a Hermitian operator. So what it says, every measurable physical quantity corresponds to a Hermitian operator. So anything that you have to measure in this framework, it has to be a Hermitian operator. The operator that you are using to extract the information about the system. Getting my point? Okay, so what you have an operator A, it is equal to A dagger, okay, adjoint of A. So A is equal to A dagger means what? Suppose you have a state, you take its complex conjugate, okay, and if it is equal to its complex conjugate, and what you do is you transpose that matrix, right? If you get the original operator from it, then you say that this operator is a Hermitian operator. That means if you have an operator, say in the form of a matrix, you take the complex conjugate of every element in the matrix and you transpose it, and you suppose it doesn't come out to be equal to the original operator, then you will say this is a non-Hermitian operator, right? So what is the postulate here? That the physical quantities that you are measuring here, they correspond to a Hermitian operator. Now let me be precise here. All the Hamiltonians, what is Hamiltonian? Hamiltonian is the total energy of the system. All the Hamiltonians are Hermitian operators. So that point should be kept in mind, right? So this is the argument of what? Postulate number 2. So let's go with an example. Now you can see you have a position operator here. Can you see it? Okay. You operate this on your state vector and you obtain the position and your state vector is back. So this x cap, which is a position operator, is what? It is a Hermitian operator, right? Because you add this position operator on the eigenstate, you get a real number and the original state vector. So position operators correspond to measuring where the particle is located. So if you use a position operator, what is your intention? Your intention is to locate the particle, right? Getting my point? You operate it on the eigenstate, your intuition is to locate the particle. Momentum. We have momentum operator, right? So momentum operators determine the particle's motion, obviously, because momentum, as we understand from classical point of view, and we have an equation for momentum operator. P cap is minus IH cross d by dx. Energy. The Hamiltonian operator corresponds to the total energy of the system, as I said. Okay, so Hamiltonian is the summation of kinetic energy and potential energy. And I told you all Hamiltonians are Hermitian operators. Now let's go with postulate number 3. Now you have gone through first two postulates. First one talking about the state vector, the next one talking about observables, okay, talking about that your operators that you will be using to operate the state vectors, they must be Hermitian operators. Now the third thing is the measurement. Now see what you have. You have the two important frameworks: state vector, observables, Hermitian operators. Now measurements yield only eigenvalues of the corresponding operators. But what is important here? When you measure something using an operator, you have an operator, you execute this operator on an eigenstate, you obtain eigenvalues. But if your operator is a Hermitian operator, you will always obtain real numbers. The eigenvalues that you will be obtaining, they will be what? They will be real numbers. So you can see here. Now for an operator A, it is acting on the ket of A, and what we obtain? We obtain a number and A. Well, A here is the real number. Getting my point? So these are the examples. This is the first example about the measurement, right? Because postulates 3 is measurements yield only eigenvalues. So when you have to measure something, you will obtain eigenvalues corresponding to those operators. The second important experiment, what is this? Double slit experiment. It's a very fundamental experiment in the field of quantum mechanics. It's an experiment through which you can understand quantum bits. You can understand a very weird nature of quantum mechanics. Now to begin with this, I tell you that you have a double slit experiment. Look at me now. You have double slit. This is a slit 1, this is a slit 2. Okay? Now you have a gun. This gun is shooting the electrons. Now your gun, if it shoots the electrons, what's going to happen? Here you have a screen. What you will find on the screen, you will find an interference pattern, isn't it? You will find an interference pattern. So you will say, come on, okay, you have shot a large number of electrons. Some of the electrons might have passed through slit 1, some of them might have passed through slit 2. Then they would have taken some kind of interference, and you have an interference pattern, and you say, come on, electrons are waves. But that's not my point. Now my point is that when you are performing this, now you repeat the same experiment. You repeat this experiment. Now you have a gun. This gun is shooting electrons. It's shooting 1 electron in 1 second. You have the slits, slit 1, slit 2. Electron 1, electron 2. What do you expect? What do you expect on the screen? You are not looking at the screen. You are not seeing what's happening on the screen. But you can sense that. You can sense that. So what do you expect? You expect, maybe if this is slit 1, you will have some maxima at slit 1, and you will have some maxima at slit 2, depending on electron. Maybe in the first case the electron is gone through the slit 1, or the electron is gone through the slit 2. Are you getting my point? So now if you will shoot these electrons continuously, what will you obtain? You obtain an interference pattern. You are obtaining what? You are obtaining an interference pattern. But you are not looking towards the experiment. You are not looking towards the experiment. So your electrons are behaving like waves. But when you look at the experiment, what do you see? You see a maxima at this hole, you see a maxima at this hole. Now what is happening? What is happening? The observation is changing the course of the reality. When you were not observing the experiment, the electron was present at both holes. It was present at slit 1, it was present at slit 2. It was making that interference pattern and you were getting a pattern on the screen. But when you look at this experiment, so how do you look? How do you look onto the experiment? You need the light to fall on it. You need photons to fall on it. When you try to look at the experiment, what you see? You see the pattern is gone. The electron is very intelligent. It's changing its job. When you are not looking at the experiment, it was showing you many probabilities. But when you are looking, when you are observing it, it's giving you just one value. This is what I mean. The double slit experiment. Detection gives a single point, not a spread wave. When you are not looking at the experiment, it's acting as a spreading wave. You have an interference pattern on the screen. Even if you are shooting one electron in 1 second. Are you getting my point? It's not the random action of the electrons I'm making on my system. One electron in 1 second. If this experiment is carried out over a million years, you will have an interference pattern. But when you will look at it, it will lose its interference pattern. Because the observation changes the state vector. Getting my point? Yes?
So how is it decided that electron किस वाले state में जाएगा?
It is when you don't look at it, you realize that it is going through both the slits. And that's a reality. And we have quantum computers, people are working on that, and they work on this principle. So when you are not looking at the system, the electron is certainly doing its job, it's passing through both the slits, making all the interference patterns and giving you an interference pattern on the screen. But the moment you look at it, your interference pattern is gone. Okay? It behaves like a point. It tells me, come on, I'm a point. I'm not a wave. I don't have a spreading nature. I'm a point particle. And you calculate those probabilities as the square of the wave function. This is the only thing that you can. You cannot extract the information from the state vector. It doesn't have the physical implications. Its physical implications come only when you calculate its probability density. And probability density is what? It is psi star. Right? So calculating that gives you the probability density. Spin of an electron. So you measure the spin, but you take a preferred direction. Preferred direction, if the preferred direction is z-axis, what it gives us? It gives us either plus half or minus half. So you have an equation for that. The state of the spin operator acting on the spin up state gives plus h cross by 2 spin up. So this is representing the state vector. Okay? This is representing your state vector. And Sz is the spin operator. Acting on this state vector leads us to what? Plus 1 by 2, plus h cross by 2. Assuming that the assumed direction is along the z direction. There is another example, that is energy levels. Okay? What we do in laboratories, we see the energy levels. Okay? We see the energy levels. So you are measuring something. You are experimentally measuring something. Only discrete energies are appearing. Do you obtain the continuous energies? Starting from state vector, then observables, then Hermitian operators. What do you obtain? You obtain eigenvalues. Getting my point? You obtain discrete energy levels. That's what you obtain. Okay? And you you know, even if you realize that this equation comes from Bohr's postulates, okay, it also comes out as a result of solving Schrodinger's wave equation for hydrogen atom in spherical polar coordinates. All right. Now, so what you have, what is in your hand when you do quantum mechanics? It is these probabilities. The probability of an outcome is given by the square of the state vector. And square is understood that what you do is basically you take an eigenstate, you take its complex conjugate, you multiply the two, and you obtain the probability density. So here, the postulate 4 is talking about probabilities. So this is what you obtain. You obtain probabilities, isn't it? You obtain probabilities. Now, probability of detection follows what? Psi square on a screen. Come on. This is the probability of detection on the screen. And what is that? That is square of psi of x. Now, assuming that I is the intensity. So this I is proportional to these probabilities. Radioactive decay, okay, alpha particles, okay, crossing the barrier, okay. So you can calculate the decay events are strongly governed by the probabilities. The alpha particle will come out of the nucleus because we can calculate the probabilities. We can say that there is this much of probability that the alpha particle has a chance to escape the potential barrier of a radioactive nucleus. And if you remember, that probability is e to the power of minus lambda t. You can have the measurement of quantum dice probability. Again, you are taking a state and taking its square. You are calculating what? You are calculating the probability. The fifth postulate, which becomes now your model, a model of a movie. Okay, it's something like, I can say, suppose you are a manufacturing company and you're designing the shirts, say t-shirts. Okay, so you use all the basic things by virtue of you design a t-shirt. Okay, then finally what you have a model, and that model will go and describe the t-shirt to the public. So here what we have, the postulate 5 is the time evolution. And time evolution is described by Schrodinger's wave equation. Because we have Schrodinger's time-dependent equation. And Schrodinger's time-independent equation is when you are assuming that there is no evolution of time. So what you have, the state of a quantum system evolves. It evolves according to the Schrodinger's equation. And this is your Schrodinger's equation, okay? IH cross dou psi by dou t is h psi, where h is the Hamiltonian operator and dou by dou t is the time-dependent energy operator, okay? The difference between Hamiltonian operator and the left-hand side is revealing the evolution of time. If you will kick it off, what you will get? If you will kick off the left-hand side of this equation, you will fall in time-independent Schrodinger's wave equation. That is h cap psi, right? Okay? So this is our basic equation, and this equation is evolutionary in nature. I mean, time evolves according to this equation. This is a free particle wave function that spreads over the time. And you can write this wave function like this. Okay? So this gives you the evolution of the wave function that spreads out. These symbols, you know all of these symbols, and you will come across these symbols as we go into the core of quantum mechanics. You will be knowing about them, like k is propagation vector, omega is angular frequency. I think you are well aware about those things. Harmonic oscillator problem, okay? This is wave function oscillates but remains confined, okay? So for that you have energy eigenvalues. This problem we have to do extensively here in this course. It is h cross omega times n plus 1 by 2. This is another example. And quantum computing, which I was talking about, what happens here is qubits evolve under unitary transformations, okay? But unitary transformations, these are time evolution operators about whom you will come to know in future, so I will not go into the details of these operators. So what we have, in conclusion, we have talked about the 5 basic postulates of quantum mechanics. Okay, so to quickly revive, what was the postulate 1? It was about the state vector. Okay, you can describe any system using a state vector. What was the postulate 2? You have observables. Okay, then postulate 3, measurement. First postulate 4, probabilities, and postulate 5, time evolution operator. There is postulate 6 also. And what is that? And that postulate plays a very important role. That postulate plays a role when you are dealing with the many particle systems, like quantum statistics, where you have fermions and bosons, okay? And what that postulate is basically the inclusion of Pauli's exclusion principle. And what Pauli's exclusion principle tells us? It tells us that no two electrons, no two fermions should be more fundamental than that of electrons. No two fermions can have same set of 4 quantum numbers. So with this, I hope I have given you a little bit of time. So with this, goodbye.